In our most recent chapter, we've been working with random variables and we've been focusing on binomial distributions. And sometimes using the formula for calculating a binomial probability is a little unwieldy, especially when we deal with large factorials like 80 factorial or 100 factorial. That doesn't always work so well with the graphing calculators. So one of the questions we might want to ask ourselves is there another way we could calculate the probability? So the question we're going to ask ourselves is, when does a binomial distribution resemble a normal distribution? And we're going to use Fathom here to help us answer that question. Here I've created a variable, and let's take a look at what formula is being used to create this variable. We're going to pretend to be flipping a coin, and we're going to be flipping the coin n times, and the probability of showing a face or a head on the coin is going to be p, and we're going to record how many successes we have from 0 up to maybe 10 if we're having 10 flips, or 20 if we're having 20 flips. So let's take a look at what's going on here. We can see that when the probability of success is 10%, in other words, the probability of seeing a face on the coin is 10%, and we're flipping the coin 10 times, we might have 0, 1, 2, 3, 4. Those are actually the most common outcomes that we might see. Actually, 1 is the most common of all of those, and that happened about 45 times. I can hit re-randomize here, and we can see this is still a distribution that's skewed to the right. Clearly, we don't want to use a normal distribution instead of a binomial distribution, and we don't really need to. But does this distribution ever appear normal? Well, let's see what happens, or approximately normal. Let's see what happens as I change the value for p here. And we'll have this march across the screen. Let's see, it seems to be looking closer to normal there, but is that really normal? I would say not quite at this point. Let's see if we can move this over here a little bit. No, it's still a little bit skewed to the right. Let's take a look at, what if it's 0.5? Well, that almost seems approximately normal. It's definitely symmetric, but not exactly normal. And it makes sense that it'd be symmetric because half of the time we're seeing heads, half the time we're seeing tails, so it should be centered at 0.5. What if we increased our sample size? In other words, what if we increased the number of trials? So instead of 10, maybe we have 25 or 30. Well, still this doesn't look like it's approximately normal. Let's see. What if our value for the probability of success changed? And we can see this marching across the screen. There it looks closer to being approximately normal. Well, in order for us to use a normal distribution calculation as an approximation, we want there to be at least 10 successes and 10 failures that we'd expect to see on average. And so let's say the probability of success was 0.5. If there were 34 flips and the probability of success was 0.5, we'd expect to see 17 heads and 17 tails on average. And that's definitely more than 10 successes and 10 failures. So as long as we would expect to see on average 10 successes and 10 failures, we can use the normal distribution as an approximation. Let's go back here. Actually, let's go over here to 90%. All right. Would it be a good idea to use a normal distribution here? And I think we can see that the answer for that is probably not. We've got some strange things going on here. Let's think about the number of successes and the number of failures. The number of failures we'd expect to see would be about 10%, and 10% of 34 would be 3.4. That's not at least 10 successes and 10 failures. For us to have at least 10 successes and 10 failures, we wouldn't be talking about a probability of success of 90%. We'd want a probability of success of around 2/3. So let's move that down here and just see what that looks like when we get around 2/3. A little bit better, but still not exactly normal, and clearly not normal on the extreme values.